Alright, welcome back. So we're going to start here by looking at Chapter 11, Section 7. This is page 511. I want to draw your attention to this figure, figure 36 here on page 511. And essentially it shows a heating curve for water. And we're going to calculate how much heat is needed to do each of these processes on this heating curve. Okay, so we're starting out with ice that has to warm up, then ice that has to melt to the liquid, then liquid that has to warm up here in section 3, and it will warm up to its boiling point where it will vaporize and turn into steam, and then we're going to warm that steam up to whatever final temperature we desire. Okay, so here's the heating curve, and we have the heat added per mole, and we have the temperature change that's experienced. But we know we have all 5 of these processes happening. We want to calculate how much heat is required for each process. Okay, ice warming up requires this amount, and this amount, and this amount, and this amount, and that amount for all those processes. Where do those numbers come from, and how do you find them? Well, so let's look at each segment one at a time. So segment 1 is melting, segment 1 is warming up, segment 2 is melting, segment 3 is warming up, segment 4 is vaporizing, and segment 5 is warming up again. Okay, so let's start with segment 1. We're going to constantly be referring back to this. Imagine we have 1 mole of ice. Okay, we're gonna pick a certain amount. We choose 1 mole because it's really easy for us to do calculations that way. At minus 25 degrees, that's where we're gonna start. So a really cold lump of ice. Now, the first thing that happens in this heating curve, segment 1, is the process of changing the temperature. And the temperature is going to continue to change up until the point where a phase change can happen. In this case, that's going to be 0 degrees, where it will start to melt. Alright, so how much heat is required to get from minus 25 Celsius to 0 Celsius? That's what we're going to calculate, and we calculate that easily by using the equation Q equals mc delta T. And in our case, since we have 1 mole of ice, which is 18 grams, we need the specific heat of water, so that's a number we're going to have to look up. In this case, 2.09 joules per mole degrees C. Alright, that might be a different number if you look it up in different ways because of how that usually works. Okay, so you may be saying to me, but I thought that number for water was 4.184. Well, for liquid water, yes it is, but for solid water, remember that's what we're dealing with here, ice, from minus 25 to 0, we have to look up the specific heat for water in the solid phase, or for ice itself. So we get 2.09. So now, when we're plugging that in, we're calculating Q, the amount of heat. We take the mass, which is 1 mole, or just 18 grams, times the specific heat, 2.09, times the change in temperature, and notice here we've got the final minus the initial. The initial one is negative, so we're keeping track of the signs and everything. And we find the amount of heat required is 0.941 kilojoules, and that was the amount listed for us on page 511 there in section 1 on figure 36 that we just saw in the previous slide. So that's where that number comes from. Okay, so keys here to remember are we're doing a change in temperature. So both of these numbers can be in Celsius or can be in Kelvin. And those have to be plugged in with the particular sign. Remember, it's a change, so we're taking the final temperature minus the initial temperature. And we're using the specific heat related to the particular sample we have, in this case, solid water or ice. This is the correct number, 2.09 joules per gram degree C. I just noticed this one said mole. But it should look like this. And you can follow along here on page 512 as the book breaks each of these down. So we get 941 joules for segment 1. Now let's look at segment 2. Segment 2 is where we're actually going to melt the sample of ice, the 1 mole sample. And the whole time it's going to remain at a temperature of 0 degrees C as we add more and more heat. So how much heat is needed to melt the whole sample? Well, in this case, remember, I can look up the delta H of fusion, which is a number given to me in kilojoules per mole. So delta H of fusion, remember, fusion means solid to liquid or liquid to solid. So we don't have to look up a delta H of fusion for ice or a delta H of fusion for water, because delta H of fusion is a phase change between those two things. So when you find fusion, you found the one you need. Later, we're going to use vaporization because that's the one we need for that process. So because it's in units of kilojoules per mole, or amount of heat per mole of substance, all I have to do is multiply by the number of moles in, and then my mole here and my mole in front will cancel out. Okay, let's see if I can draw that up for you. We're going to take moles, number of moles, doesn't work so well drawing with a mouse. And we got kilojoules per mole. Ugh, what kind of J is that? Kilojoules per mole here on this side. So the mole we're going to multiply by cancels the mole on bottom, leaving us with kilojoules, or Q, which is what we were looking for in the first place. All right? Hopefully that was helpful. So all I have to do is multiply the number of moles times the delta H of fusion for this particular sample to find out the amount of heat. In this case, 6.02. What's going on here? And there we go. Okay, so 6.02 kilojoules for segment 2. So now how much heat was required to go from minus 25 to melting my entire sample? Just segment 1 plus segment 2. These two amounts of heat. Now, what's segment 3? Going from 0 degrees all the way up to the point of vaporization, or the boiling point. And in the case of water, that's going to be from 0 all the way up to 100. So here we have a temperature change for liquid water. So I need the specific heat of liquid water, which is the 4.184. That number is not correct. But that one is. Okay, so disregard my number here. I apologize for that. It should be 4.184, all right? Okay, so we can calculate how much heat is needed. Take the number of grams you have, since we have 1 mole, it's just 18 grams, and multiply by 4.184, and then the change in temperature, the final, which is 100 degrees, you want to heat it all the way up to 100, minus the initial, which is 0, and then you'll get some particular number, 7.52 kilojoules. That's the amount of heat needed for segment 3 from raising the temperature from 0 up to 100. Why did we stop at 100? Because that's where the next phase change happens, and that's what segment 4 is. So here we're going to do the same thing we did for segment 2, except in segment 2 we were doing delta H of fusion, and now in segment 4 we're going to do the delta H of vaporization, or vaporization. Alright, so how many moles do I have? In this case, just 1, so it's kind of boring. Just take 1 times 40.7, and that leaves you with 40.7 kilojoules total for segment 4. Alright, now we know how much heat was required for segment 4. And now segment 5 is just changing the temperature up to whatever amount total you want. So in this case, from 100 to 125. So we're going to change by 25 more degrees. So do the same thing, Q equals MC delta T, except our C here needs to be the value for steam, which is 2.01 joules per gram degree C. So when you do the multiplication this way, the final minus the initial, you get 0.94. So what's the total amount needed to do this entire heating curve? All we have to do is add all 5 segments together, and we know how much heat is required to take a sample of ice from minus 25 all the way up to steam to 125 degrees C. We have to account for each phase change and for each temperature change along the way. So let's practice on a different kind of substance. So here we've got benzene. How much heat in kilojoules is needed to raise the temperature of 12 grams of benzene from minus 10 to 25. Now, since we're not working with water, we're going to have to go look up all the important values, so I just give them all here for you in a table. You're not expected to memorize all these numbers. They will typically be given to you to answer whatever problem you need. Okay? Or you'll be solving for them, and you'll have enough information to do that, right? Okay, so we've got specific heats of solid, liquid, and gas, the melting point, the boiling point, delta H of vaporization and of fusion, and we know the molar mass, so we don't even have to go and add that up from the periodic table. How many grams per mole, which is going to be important for us because we only know that we have 12 grams. Okay, so we're going to take it one step at a time, starting at minus 10. At minus 10, is benzene a solid, liquid, or a gas? Well, its melting point is 5.5. So our segment 1 is going to be from minus 10 to 5.5. So we're going to find the amount of heat to change the temperature of 12 grams of benzene from minus 10 to 5.5. Once it gets to 5.5, what's going to happen? Since that's the melting point, now all the extra energy we're adding in is going to go to melt the sample. So we're going to look at the heat of fusion, and we're going to use that for segment 2. And segment 3 is going to be changing the temperature of the liquid from 5.5 up to 25, up to, the boiling point is above the temperature we want. So I guess we can stop at 25 and be done there. We won't even need the specific heat of the gas or the heat of vaporization because we're not raising the temperature up that high. So let's look at those particular segments we just talked about. All right, segment 1, Q equals mc delta T, to change the temperature up to the melting point. So from minus 10, the initial temperature, to 5.5, the final temperature. Notice I'm putting in the specific heat for solid benzene, multiply by how much benzene you have, 12 grams, and then you can find the amount of heat required to make that temperature change. That's segment 1. Segment 2 here is going to be phase changing from the solid to the liquid. So I have 12 grams, and I'm converting that to moles. This is my molar mass, 78.11 grams per mole. And I'm doing that because I know this number in kilojoules per mole, and I need moles to cancel here. So I'll be left with 1.51 kilojoules at the end. So 12 grams, if my delta H of fusion is 9.8, will require 1.51 kilojoules of heat to melt it. Now once it's melted, I'm going to have a third segment to change its temperature from melting up to 25 degrees. So I go back to Q equals mc delta T, except this time I plug in my specific heat for the liquid sample and my final temperature and my initial temperature, and I get 0.3978. And all I have to do now is add all those together because the problem asked me how much heat is required to raise the temperature from minus 10 to 25. And the answer here will be the sum of these three, which is 2.1 kilojoules. So I have to put in 2.1 kilojoules in order for me to, actually change the temperature like that. Okay, this brings us to the end of section 7 on page 513. So we'll end our video here and move into section 8 in the next one.